right, good morning, ninth grade. I hope y'all are doing well. That you guys aren't too bored with everything that's going on, and that you're being able to keep up with everything as far as each of your classes go. I'm a little more casual today. I didn't really feel like getting too dressed up to do a video, so you get me in my Buckeyes shirt. Go Bucks. Sorry for the rest of you that your football teams aren't as awesome as mine. Anyway, moving forward, we're going to pick up with section 2 of your class notes for chapter 14. We started talking about magnetism in the last video for you, and today we're going to look at really why do magnets work? What about them? What feature makes them work so well? Why are they able to stick to iron or steel or a derivative of those things so well? All right, so here we go. Letter A, atomic magnets. Magnetic fields are produced by the motion of electrons, okay? We talked about electrons many moons ago at this point. But if you remember, electrons are the negatively charged portion of an atom, and they circle the nucleus of the atom in random patterns of motion. And so magnetism is caused by the motion of the electron of an atom, okay? So electron spin is the most important cause of magnetism in magnetic materials. The direction that the electron is spinning and the speed that it is spinning with are going to be some of the, they're the two major things that are going to affect whether or not a material has the ability to be magnetized or to have a magnet stick to it. So let's look at electron spin. Let's break that down. Some electrons spin clockwise and some spin counterclockwise. It really depends on the substance. It depends on whether or not the electrons of that substance will spin counterclockwise or clockwise. Now, a lot of atoms actually have both electrons that spin clockwise and electrons that spin counterclockwise. So with most atoms, the magnetic fields oppose one another and cancel each other out. So what that means, I need a drink, guys, sorry. So what that means is, let's break it down. Let's say an atom has 10 electrons, okay, just for argument's sake. It has 10 electrons. In most atoms, what will happen is 5 of those electrons will spin clockwise and 5 of those electrons will spin counterclockwise. And so because there's an even number, both spinning opposite directions, they balance each other out, and it doesn't allow a magnetic field to be created because those electrons are in equilibrium pretty much. They're balanced out. They're neutral with one another. Unpaired electrons, however, is where we get our magnetism or our magnetic fields from. Unpaired electrons are what create magnetism. The more unpaired electrons there are, the more magnetic a substance will be. So let's say we have 11 electrons in an atom this time, all right? So if 6 of those electrons are spinning clockwise and 5 of them are spinning counterclockwise, well, you have one atom that is going to be unpaired, okay? If you pair everyone up, okay, you'll get 10 that are grouped into pairs, but then you have one left over that is unpaired. That unpaired electron allows a magnetic field to be created. Now, if you just have one unpaired electron, it's not very strong. You're not going to have a very strong magnetic field. You're probably not even going to notice that a magnetic field is being created. However, the more unpaired electrons that you have, all spinning the same direction, let's say we have 30 electrons, okay, and 25 of them are spinning clockwise and 5 of them are spinning counterclockwise. Well, if you think through the math here for a second with me, okay, so you're going to have 10 that pair up, so 30 minus 10 would be 20 left over. So you're going to have 20 electrons spinning, all spinning clockwise, that don't have a counterclockwise electron to pair up with. All right. So because they don't have that counterclockwise electron to pair up with, you have a lot more unpaired electrons, which means you're going to have a lot bigger chance for a magnetic field to be created. Hopefully I didn't confuse you guys with that. Hopefully it makes sense. You can always read your textbook. You might be able to grasp the way the textbook explains it a little bit better than me. But you can check that out in chapter 14, section 2 of the 14.2. You can check that out in the textbook if you need to read that for a better understanding. Domains. Now, a domain is a group of aligned atoms that have a single magnetic field. Domains are very small and most are not noticeably detectable. When billions of domains line up, a detectable magnetic field is created. This means that a magnetic field is the sum of the fields of thousands of magnetic domains. So, a domain looks not just at one single atom, but at a bunch of atoms and how those atoms all line up with one another and how the electrons in those atoms pair up with one another, okay? As stated, most domains are pretty small and you're not going to notice the fact that a domain has been created. I would guess you probably go throughout life every day without even realizing that magnetic domains exist all around you, all right? But if there are billions of them that line up, a detectable magnetic field is created, and this is when you can stick things to the refrigerator or to a steel desk or anything that's magnetized, really. The domain theory. This is how scientists classify our understanding of what makes a magnet work. Everything is grouped under the umbrella name of the domain theory. A magnetic substance forms a magnet only if its domains are mostly aligned. Now, same thing with electrons, okay? Remember, electrons have to be paired up in order for the atom to become magnetized. Well, with domains, it's the same thing. You have to have more domains paired than unpaired in order to create the magnetic field. Types of magnetic materials. We're going to look at 3 types here for you. And each magnetic material has a, what's the way I want to put this? Each has a strength of magnetism to it, or each has a different ability to be magnetized. I guess that would be a better way to put it for you. So, you have diamagnetic substances. These are substances that possess weak magnetic fields because of the motion of electrons around the nucleus and have no unpaired electrons. So these are the ones, you don't have unpaired electrons hanging out, so they are very weak magnets or have no ability to be magnetized because they have no unpaired electrons, okay? They are slightly repelled by either pole of a magnet. The magnet's going to push back against them. It's going to go away. It's not going to try to stick to it. All right, a good example of this is gold. And if I were to, just for example's sake, if I slide my wedding rings off, let me see if I can illustrate this for you really quickly. Hi, I'm back. Sorry. Okay, so for argument's sake and for illustration's sake, my wedding rings are made of white gold, okay? So if I were to take this magnet that I had sticking under the edge of the desk, that's what I had to go get. So sorry for the blank screen for a minute. But if I were to take this magnet and try to stick it to my ring, all right, you will notice nothing. If I were to let go of the magnet, it would drop and fall to the ground, okay? Because gold is a diamagnetic material. It does not attract the magnet at all because there are no unpaired electrons in my ring. All right, you have your paramagnetic substances. These are substances that have only one unpaired electron per atom. They're weakly attracted to a magnet. A good example of this would be aluminum. If I were to take some aluminum foil and I were to stick it to this magnet again, okay, if I would have thought ahead, I would have brought some foil from home for you guys, but I didn't, so sorry. But if I were to take this magnet and stick it to foil, it would kind of stick a little bit, but it wouldn't be significant enough for me to let go of the magnet and the magnet stick to the foil. And then you have your ferromagnetic substances. These are substances that have several unpaired electrons per an atom. They're strongly attracted to magnets. The best example of this is iron. If I were to, my desk is a steel iron alloy. Anyway, if I were to stick this to my desk over here, hopefully you can maybe hear that, but it sticks to the desk. We're gonna move, sorry if I make you sick. We're gonna move, and where's it at? You can see it sticking right there to the side of the desk, just as I stuck it on. Hopefully you can see that. All right, and sorry if I made you sick with the video moving around. But hopefully, just for argument's sake, you guys can see those things, have some examples to refer to. Substances that are magnetically soft. These are substances that are quickly magnetized, even by weak magnetic fields. A good example of this is a needle. If you take a magnet, okay, if I were to take this magnet and I were to have a needle here and I were to rub this magnet up and down very, very quickly against a needle, what would happen is the needle would become magnetized for a brief period of time, and I would be able to stick that needle to the side of my desk. And eventually, what would happen, because either you touched it or it just loses the magnetism, the needle would fall off the desk because it lost the magnetic field. But it's a magnetically soft material. It allows me to create a temporary magnet out of it, okay? Substances that are magnetically hard. These are substances whose domains strongly resist changes in the direction of their magnetic fields, and these create permanent magnets, aka what you have here, well, what I have here in my hand, what sticks to your refrigerator. All of those are permanent magnets, okay? They are substances that have been made. They don't allow for a change in their domains, okay? And so no matter what I wanted to do, I could not demagnetize this. It's going to stay a magnet. It's a permanent magnet, okay? 3 methods of magnetization. Think back to that needle that I was telling you about that I could turn into a magnet if I wanted. All right, so magnetizing by contact. This would be what I would do to magnetize a needle, okay? I would magnetize it by contact. This converts a steel needle into a permanent magnet by stroking it with another magnet. This forces the domains of the needle to align with the domains of the magnet, creating a magnetic field around the needle. Like I said, I could magnetize that needle, stick it to my desk, and it would stay there until I touched it, moving those domains out of line and allowing the needle to lose its magnetism. All right, magnetizing by induction. This occurs when a very strong magnet is held near a needle and it magnetizes the needle. No touching is involved. If I were to take this magnet and hover it over a needle, okay, the needle would start to try to rise up to meet the magnet, okay, and I could stand the needle up without ever touching it using the magnet because it's being magnetized by induction. We talked about induction when we talked about electricity, all right, so if you can think back to that a little bit. And then magnetizing by electricity. This is when electricity flows through a wire and a magnetic field is produced around that wire. And magnetizing by electricity creates what we call the electromagnet. Okay, this is a device that produces a strong magnetic field when electricity passes through it. And just some facts here on the strength of an electromagnet for you. The strength of a magnetic field produced by an electric current is directly related to the square of the current. So, weaker current, equals weaker magnetic field. Stronger current equals stronger magnetic field. That's all that means. All right, the strength of an electromagnet is proportional to the number of loops of wire in a coil. All right, in an electromagnet, what happens is there are loops of wire around an armature, basically, okay? And what happens is if you only have let's say you have 3 loops versus 9 loops, well, the strength of the magnet with 3 loops is not going to be as strong as the magnet with 9 loops in that wire, okay? The more loops, the more strength, the more chances the magnetic field has to be created. And then doubling the number of loops in a coil will double the strength of that electromagnet. Demagnetization and deflecting. Now, magnets can lose their strength or lose their magnetization completely. And one way that a magnet loses its magnetization completely is by being heated past the Curie point, okay? The Curie point is the temperature at which a ferromagnetic material's domains disappear completely. Above this point, atoms are vibrating so rapidly that their domains can't align, okay? Think back to when we talked about kinetic energy with me, okay? I know that was a while ago, so think with me. With kinetic energy, the warmer an object is, the more kinetic energy it has, right? Think of a gas. Gases are warmer than solids, so the molecules of a gas move around a lot more freely. All right, well, with a magnet, when you heat it past the Curie point, pretty much what happens is the magnet has so much kinetic energy that the domains, they're bouncing all over the place, and they don't even have a chance, even though they might be paired domains, okay? There's too much heat for them to pair up with one another. The heat pretty much just keeps them bouncing all over the place. So heating an element past its Curie point is the best way to make a magnet lose its magnetization. All right, storing magnets improperly can also lead to their demagnetization. If you guys have ever stayed in a hotel before, okay, you might have noticed that if you keep your room keys, you know, the keys that slide in and the light blinks green and you can open the door, all right? Hopefully you guys know what ones I'm talking about. Well, if you take those keys and you store both of them together, or you store them maybe next to a credit card or next to even your cell phone, what can happen is the other card or the cell phone can demagnetize that room key. And it's because the room key was not stored properly, okay? So then you have to go down to the desk, you have to get it remagnetized, and use it all over again, and make sure you store it properly the next time. And then the deflecting force, this is the force that exists in a magnetic field that causes a moving electric charge to deviate from its original path. The deflecting force, this can be something in the field that just is basically blocking the path of magnetism, so it doesn't allow the magnetic field to continue, all right? And that's where we're going to stop with this video. I know this was a lot of notes. This really is about 3 days worth of notes, guys, so I'm probably not going, this is probably going to be I'll probably post this video early on next week for you, and then post another video later on in the week. So you'll have about 3 days to go through this video and get these slides down. Take your time, make sure that you're getting these slides down, because remember, when school starts back up, I am going to be going through your notes, and I am going to be checking to make sure that you got the notes down. I will also, over the next couple of weeks, I will also be sending home some worksheets that have to do with your notes. So if you don't have them written down, it could cause problems for you. As always, if you guys have any questions, email me or send me a message on the LMS dashboard, and I will get back to you as soon as I can. I miss you guys. I'm praying for you. Have a good day.